This is Introduction to Networking. This course, in addition to helping you understand the concepts of data networking in general, will also get you prepped to take the Cisco CCNA exam. But for now, I want to move on to the meat and potatoes of data networking and look at how we dissect communication into components so that we can better understand it. Data networking, in my opinion, is actually quite simple. However, I'll qualify that and say that it's simple in its individual components. It is very complex when we connect all of these individual components together. So what we need is a method for understanding and dissecting and looking at each of those individual components. So what I want to do here is identify the components of communication that we use in our day-to-day life so that we can use that as an analogy to see how that works in data networking. We're going to categorize each component. We're going to see how protocols emerge from these categories. And then we're going to look at see how the protocols and models can be used to better understand how networking works. We're at a party, all right? There's balloons flying. In walks Homer. Shortly after, a woman walks in. Homer sees this woman and says, "Oh my gosh, I have to go talk to this woman." So Homer walks over and introduces himself. He says, "Hi, I'm Homer." Marge says, "Hi, I'm Marge." And Homer and Marge begin a conversation with each other. Now, Homer and Marge can converse with each other because they're using a kind of local addressing. While they're at the party, Homer and Marge are going to use their names to communicate with each other so that Homer can talk to Marge, and Marge will know that Homer is talking to Marge because Homer is using a local address of Marge, and that way Jill won't get confused and think that Homer is talking with Jill. Now, maybe Marge and Jill are standing right next to each other, and Homer's talking and he doesn't identify who he's communicating with. So Jill has to stop and ask and say, "Hey, Homer, who are you talking to?" And Homer can say, "Oh, I was talking to Marge." So now Jill knows that that conversation is not meant for her. So our local addressing is our name. So if we start to categorize this little party that we went to, we have local. We have a category of local, and we're going to use our individual first names for that local addressing. So the party's wrapping up. Homer and Marge had a great time. They chatted all night. Party ends. Homer says to Marge, "Marge, may I please have your phone number?" And Marge says, "Oh, yes, Homer, here you go." And now Marge gives Homer her phone number. Homer now has Marge's global address because now Homer can use that phone number to contact Marge from any place on the planet that has a telephone. So he knows that Marge has a local address of Marge, and now Homer knows that Marge's global address is 867-5309. So if we categorize this, now we have a global address, and that's our phone number. So we have a local address, our name, a global address, our phone number. And if we think about it, our local address, our name, allows people in the same room as us to call attention to us and identify us. And our global address allows us to communicate with others when we're not in the same room with each other. Let's continue this. Right? So Homer gets excited a couple days later. He waits the mandatory 6 days and he wants to call Marge. So what does Homer do? He has Marge's global address. He just can't pick up the phone and start shouting into the phone and expecting that Marge is there. He has to go through a very special process to establish communication with Marge when he's using that global address. And that looks like this. He has to pick up the phone. He has to wait for the dial tone. He has to dial the number. After he dials the number, he's going to wait for the phone to ring. After the phone rings, Marge is going to pick up the phone. They're going to start the conversation. Marge is going to say hello. Homer says hello. Now we can send any information we want. During our conversation, we have cues that allow us to keep the conversation moving forward correctly. Those cues might be, I see, as acknowledgments that the message was sent and received. There might be a statement of, "I don't understand," or "You're breaking up," meaning, "I don't get the message, can you repeat it?" Or we may have the end of the conversation saying, "Goodbye, bye, see you later," and shutting the conversation down. Now, all these pieces, the setting up of the conversation by Picking up the phone, waiting for the dial tone, dialing the number, waiting for it to ring, waiting for somebody to answer, saying hello, hello. All that stuff does not add to the conversation at all. There's no data being transferred at all, except acknowledgments that data was transferred or a protocol to establish or end the conversation. So although we're sending messages, our messages are meant to keep the conversation alive and not necessarily to transfer information. So if we look at this, we can create a new category called cues. And our cues are going to be what is used to set up and tear down our conversation, especially in the global sense when we're using the telephone. It's also going to be used to keep the conversation moving by saying, yes, I understand, or no, I don't understand, please repeat that. Last, we have our actual conversation. How was your day? What's the weather like by you? I like talking to you at the party. I think your hair is pretty. Things like this, right? This is our conversation. This is the data that we're actually sending. This is the content. We just need all that other stuff in order to send these messages. In order to have a very personal conversation with Marge, we need to know her local address, which is her name. If we're communicating with her globally, we need her global address, her phone number. We need a method of establishing global communication using that phone number, as well as some cues in that conversation to keep it moving. And then with all of that, then we can actually start to send data, which is our conversation itself. So if we add this to our list here, we're going to add data as a component here, and this is going to be our conversation, right? The communication that we transfer back and forth. There's actually one more category that we didn't talk about. We actually talked about it in the previous module of this video, and that was the media that we're using. In this case, the media we're using is air and wires. The air we're using to vibrate our vocal cords to send out our messages. The wires is what the telephone is converting our vibrating air into the electrical signals that go over the wires. So we have these 5 categories, and we have individual components that happen in each of the categories. This is going to tie directly into what we're doing in data networking. If we look at a protocol is a set of rules used to move information between 2 people or devices. Now I'm talking about data communications protocols here specifically. So when we talk about data communication protocols, we're talking about a set of rules. And if we think about it, we have a protocol that we use every time we dial the phone. And that protocol, if we do not follow that protocol precisely, our phone call will not work and will not be able to connect to the person with the global address we're trying to reach. Throughout learning data networking, we're going to learn about protocols that we use to communicate. Those protocols can show up in all kinds of forms, right? They have all kinds of names. Usually they're 3 or 4 letter abbreviations. Sometimes they're whole words like Ethernet. Ethernet is a protocol we use for communication. SFTP, Secure File Transfer Protocol. HTTP and HTTPS are probably the ones that you're most familiar with. You may have heard of IP and TCP and UDP and BGP, right? We're going to cover all of these protocols, and by the end of the series, you are going to know the details of what all these do, which is really surprising because there's an incredible amount of detail to learn in all of these. But the nice part about it is when you look at these protocols individually, they're actually not that complex. The complexity comes with the interaction between the protocols in order to make it work. So how do we solve that complexity? We introduce a communications model. The communication model that we introduce is used specifically for organizing information transfer into its components. Just like we did here with Marge and Homer meeting at the party, exchanging a phone number, and then using that to establish communication in a global sense, we were able to break all those pieces down into a communication model so that we can better understand it. These communication models are going to help us then identify and organize everything so that it makes it very easy to dissect the complex beast of data networking. To wrap this up, we've identified components of communication as they relate to data networking. Name, telephone number, conversational cues such as the teardown and setup of a conversation, as well as the cues that keep the conversation moving. And then we have our actual data, right? These are the components of communication. We categorize those components. We saw that protocols emerge from those categories. Things like dialing the telephone is a protocol we use. And then we're able to use those protocols and then put them into our organizational model so that we can understand exactly how the communication is working. Now, this wraps up my little story of Homer and Marge meeting and dissecting their conversation. Let's go look at how Homer and Marge's dissected communication process here applies to data networking so that I can give you some tools to understand how the rest of the course is going to work. Welcome to Pluralsight. I'm Ross Bagurtis. In this next module, we're going to look at network communication models. This will continue the conversation we started when we were talking about dissecting communications in the previous module. Our goals this module are to map our communication dissection that we did last module to data networking communications. I want to use that as a launching pad then to talk about the OSI model and the TCP/IP model for network communication organization. These are literally critical in understanding how networking works, and I want to give you as much information as I can so that you can make use of these models to understand data networking. Now here's the model we built up last module. We talked about Marge and Homer meeting at a party and then later on conversing over the telephone. We talked about the local addressing with the names, the global addressing with the phone number, the cues, which were just keeping the conversation going, and our data, which was the conversation itself. This time I want to start with data and work our way up these data transmission categories and see how it maps to data networking. So first we're going to start with a website as our data. So we can have websites or email being transferred here. We're going to start with a website. We're going to assume that our user here wants to go to pluralsight.com. So she types in www.pluralsight.com into her computer, and effectively what that does is it goes and grabs Pluralsight's web page and it brings it down to the local computer where our user is working. So effectively we have a computer where our user is sitting. They say, "Give me the website, please." And Pluralsight.com responds with, "Here's the website." It is literally a document, all right, like a Microsoft Word document or an Excel spreadsheet. The website that we're getting from Pluralsight.com is a document that we're downloading so that we can view it on our local workstation. So the data here is our website. In order to get that website, though, we have to have these cues like we do in our conversation. We have to have a way of setting up the conversation, of maintaining the conversation, and tearing down the conversation when it's over. So in this case, we need some mechanism to do that in networking, and that mechanism we use is called TCP, or Transmission Control Protocol. TCP is a fundamental protocol in data networking. Understanding TCP will make you a hero someday on your data network. The more you understand about TCP, the better you'll be. And there is a crazy amount of information to be learned about TCP. We're going to start with the super simple part here and see how TCP sets up a conversation between our workstation and Pluralsight. Now, before Pluralsight.com can send us the website, and actually even before we can even ask Pluralsight.com for the website, we have to establish a session in order to begin that website transfer. And the way we do that is we send a message from our workstation before we request the website. We send a message called a SYN message, S-Y-N, for synchronization. And what that synchronization message does is it says to the web server, Pluralsight.com in this case, "I want to make a connection to transfer data." And the server says, "Yeah, I'm available for that." So what the server will do is it'll generate a message called a SYN-ACK to acknowledge the synchronization message, telling the workstation, "Yeah, I'm available for transferring data." The workstation will finally respond with an acknowledgement or an ACK saying, Okay, I'm about to send data. I understand that you're open to do it. I'm going to send you something. Now, if you talk to network nerds, oftentimes they will actually use ACK, instead of yes, or I understand, or I got it, right? It's the nerdiest way to acknowledge conversational transmissions in real life. But this process of sending a SYN, responding with a SYN-ACK, and then responding again with an ACK, that's called a three-way handshake and is what we use in data networking in order to establish a session so that we can transfer information. This is exactly what Homer did when he called Marge, right? He didn't do a SYN-ACK. What he did is he picked up the phone, waited for the dial tone, dialed the number, wait for it to ring, wait for Marge to answer, say hello, he says hello, then they can transfer data. We're doing the same thing here. Then we can say, oh, okay, send me the website, please. And then Pluralsight responds and says, here's your web page. So what we saw now is that we have our website that we want to transfer, but in order to transfer that website, we have to do a three-way handshake with TCP. So hopefully you can see where this is going. We're going to quickly move now into the global addressing. Well, in global addressing and networking, we use something called Internet Protocol, or IP. At this point, hopefully you've heard of an IP address. If you've not heard of an IP address, don't worry. We're going to go into the nitty-gritty details of what an IP address is, how to view it on workstations and routers. Understanding IP is fundamental to understanding data networking, just like understanding TCP is. If we look at our global layer here, we have Internet Protocol, and what that means is that we're going to give something called an IP address to each device on the internet so that every device is globally reachable, meaning any device can communicate with any other device if they know the IP address of the device they're trying to communicate with. Now, we have a sophisticated system called DNS, or Domain Name System, that will actually act as a telephone book and convert a name like Pluralsight.com into the IP address 198.51.100.80 for us. We're going to learn more about that later. For now, what we need to know is that in order for our workstation to be able to send that SYN message to Pluralsight.com, it has to know the IP address of Pluralsight.com. So what we do is we take our SYN message and we actually address it with a source and destination IP address, just like addressing an envelope that you're ready to send in the mail. We put a to address, which is where we're sending it to. In this case, it's Pluralsight.com at 198.51.100.80. And we're sending it from my workstation, which is at 203.0.113.10. Now I have a mechanism here of sending the SYN message. And Pluralsight.com can then use that global address that it received from my workstation to respond back to my workstation. And then we send our ACK telling Pluralsight, yep, we're ready to send data. Then we're going to send the data saying, website, please. And Pluralsight.com will respond with the document that is the web page on our workstation. At this point, you might be saying, geez, Ross, you keep repeating this. Yeah, I do. And the reason is that all of data networking is repetition again and again and again and again and again. As a matter of fact, if you read the instructions on a shampoo bottle, it says lather, rinse, repeat. That's what we're going to be doing here in data networking, is lather, rinse, and repeating. If we can get that down pat, we have the mechanism we need to understand data networking. Let's go on to the next layer, which is our local layer here. And in our local layer, when we had a conversation, we were using our names. Here, we're going to use something called Ethernet. In Ethernet, we need local addressing. The local addressing we use in Ethernet is something called a MAC address. An Ethernet MAC address is an identifier for Ethernet communication locally. Now, in order for us to be able to send a message from our workstation to the global address at Pluralsight, 198.51.100.80, I need to take that global addressing and I need to put it in another little envelope, a container, that has my local addressing as well. So what I do here is I'm going to take my source and destination addresses, my to and from IP addresses, the global address, and I'm going to readdress that at the local layer so that my workstation can actually send the message to the device that's responsible for getting it out to the internet and eventually to pluralsight.com. And that is my router. If you have internet access at home, you will most likely have this device in your network. The device that's in your network is going to have an IP address on it, just like this one does. This one has an IP address of 203.0.113.1, and that's called our default gateway. A gateway and a router are the same exact thing. As a matter of fact, it's two different names for the same exact device. So our default gateway is where we send our messages when they're going out to the public internet. In order to get our message to the default gateway, we need to know the local address of it. So just like when Homer called Marge using Marge's global phone number, when they answered the phone, they still used their local names to talk to each other. And this is a bit similar to that, because what I need to do is I need to send my message to the router using the local addressing. When it gets to the router is going to see that this message was destined for it based on the local addressing, and it's going to throw that local addressing away and put in new local addressing so that when the router sends the message out its other interface, the one that's connected to the internet, it can actually get that message locally to the next device on the internet that needs to get it, and it'll keep putting this message in new little packages with a local address in them to get from one router to the next router to the next router until we get all the way to pluralsight.com. We don't know what those local addresses are. We'll never be able to see them. They're invisible to us on our local network, and there's a good reason for that. The good reason for it is way too complex to explain now, but just understand that when we're sending our messages from one device to another device, we always have to put that message into some kind of container that has a local addressing scheme attached to it. Once we get that message to our router, then the bigger picture can start to form, because with those local addresses and putting the SYN message that's addressed globally inside of another container with our local addresses, that's what's going to allow it to propagate over the entire internet. I've taken those addresses out of here just to keep the complexity down, so that we can see that we're sending our SYN, SYN-ACK, ACK. Then we can finally request the website. The website gets sent back, and we can see the website. So if you look back at our categories here, we have the website that we want to transfer, which is pluralsight.com. In order to transfer it, we need to use a three-way handshake to build a session so that we can ask to have the website transferred. In order to build that three-way handshake, we need to know global addresses, which are our IP addresses. In order to use the IP address, we have to put that whole chunk of information with the to and from and the three-way handshake information, even our website, we all have to put that in a container that's addressed locally. That's Ethernet, and there we're using MAC addresses. And all of that stuff gets sent out over wires, radio, or glass via fiber optics. If we look at our very simple network here, we have a wire. Maybe we have wireless, if we're using wireless in our home. Most likely, our data is transferred over fiber optic at some point in time between your workstation and the time that it gets to pluralsight.com. So we have our wire. We use the wire to transfer our local addressing information, which contains our global addressing information, which contains our SYN message to build the session, which is eventually going to allow us to get the website. So we have our global addressing, we send our SYN, we send our SYN-ACK, we send our ACK. We ask for the website, Pluralsight sends us the website. So we need wires, radio, or glass. We need Ethernet, we need Internet Protocol, we need TCP. All of that has to be in place simply to be able to send the website. The dependencies of these pieces show up in exactly this order. In order to send the website, we need to use TCP. In order to use TCP, we have to use IP. In order to use IP, we have to have some local mechanism for communication. In this case, it's Ethernet. There are other methods for local communication. We will get into those in depth throughout this series. For now, understand that Ethernet is a very common one. It's the one that if you have internet access at home, you are most likely using Ethernet in your house to communicate with your router to get out to the public internet. And all of that local stuff needs wires, radio, or glass to communicate. This maps very nicely into the OSI model. The OSI model stands for Open Systems Interconnect. It was developed in the early 70s, so it's old, but it's effective. There's a few pieces that are so arcane we don't use them too much, and we actually don't even talk about them too much. We'll get to that in a second. For now, let's map out our communication that we just covered for moving a website from one device to another, and let's look at how the OSI model maps to that. If we start with the first layer here, we have the physical layer. That is literally the physical components of it, the media, the wires, the radio, the glass. We have the next layer, which is called the data link layer. The data link layer is a bridge between internet protocol and the wires, radio, or glass, the physical layer. In this case, Ethernet is our data link layer. It uses MAC addresses for the addressing. It's what we do for local communication. Ethernet gets our data from one device to another device, all within a local network. Next, we have the network layer. The network layer is a global layer, and it uses Internet Protocol, or IP. It uses IP addresses, which are a global addressing scheme. This is where routing takes place, where we actually have our routers, the devices that move traffic across the internet. Routers are a device at the network layer. Move up one layer, we're at the transport layer. This is where TCP exists. There are other protocols that exist at the transport layer, like UDP as well. We will cover those in detail as we go through the course. For the time being, we need to know that the transport layer is responsible for setting up this conversation between the two devices. TCP is the protocol that operates at the transport layer that sets up conversations and maintains them. And then last, we have the application layer. And when we put this all in together, this is the OSI model. The application layer is where we transfer our data. So this is where we're going to transfer websites, emails, other files. It's going to happen at the application layer. Another model called the TCP/IP model, which exclusively focuses on the TCP/IP protocol suites and organizing them into layers, much like the OSI model did. Why do we have an OSI model and a TCP/IP model? Well, in the early 70s, TCP/IP really wasn't a thing yet. TCP and IP didn't come out as official protocols on the internet until the very early 80s. Any type of computer networking that we did prior to the early 80s and even into the 80s oftentimes was able to be mapped to the OSI model because we weren't using Ethernet. We weren't using IP. We weren't using TCP. Websites weren't even a thing in 1975. Websites didn't come out until the early to mid-90s. A lot of these technologies that we use are much more easily related to this new TCP/IP model versus the OSI model. In order to understand networking and pass the CCNA exam, you'll need to understand the distinction between the two. I moved that table over a little bit and we'll add on another column here for the TCP/IP model. The TCP/IP model starts with the network interface layer, and that's kind of a combination of the physical layer and data link layer in the OSI model. The network interface layer takes into account the physical component that we're going to transfer the data over, as well as the protocol we're going to use to transfer the data over that medium. So in the OSI model, we say at the data link layer we have Ethernet, and then at the physical layer we have the physical medium that we're going to transfer our Ethernet traffic over. In the TCP/IP model, we just call that the network interface layer, and we combine it all together. This is a very effective way to do this because outside of talking about are we using wires, radio, or glass, we have a type of Ethernet that operates over all three. We have Ethernet that operates over wires. We have Ethernet that operates over radio called wireless Ethernet or 802.11. And we have Ethernet that operates over fiber optics. So the TCP/IP model is very effective at identifying this. The next layer at the TCP/IP model is called the internet layer, which maps directly to the network layer. The transport layer and the transport layer have the same exact name and the same exact function, as do the application layer and application layer of both models. Now I cheated here. I actually left out two layers of the OSI model, and those are the session layer and the presentation layer. Now, when we're talking about data networks and understanding how data networking works and how packets get moved from one device on a network to another device on a network, the session and presentation layer often will add in a layer of complexity and confusion that will make the rest of this model completely useless. So what I tend to tell students is to not worry too much about these two layers. Are there protocols that operate here? Sure. At the session layer, technically we have SSL, which we use in HTTPS, and that's operating at the session layer. Are there protocols at the presentation layer? Sure. There's a protocol called Citrix ICA. It's used to connect a client to a Citrix server to get remote access to applications and desktops and things like that. In the early 70s, when the OSI model was developed, there were some competing standards out there yet, especially for how we encode text into binary characters that can be stored and sent on computers and over data networks. IBM, as normal, came up with their own proprietary standard for encoding letters on the keyboard into these binary bits, and the rest of the world came up with an open standard that everybody could use. These standards were ASCII, ASCII on the open source side that everybody could use for free, and EBCDIC, EBCDIC on the IBM side. So if you were a big business that tended to do business with IBM, chances are you would purchase some computer hardware that would only support EBCDIC. And chances are you would want to communicate with another organization that maybe purchased non-IBM equipment, so they were using ASCII. So there had to be some protocols written there that operated at the presentation layer to change our format from ASCII to EBCDIC. We don't need these presentation changes anymore. So when we do encounter presentation or session layer protocols in data networking, it's typically because those protocols meet the standard that OSI set forth when they wrote the model. So the Citrix ICA protocol makes use of presentation layer features. SSL, used in HTTPS, makes use of session layer features as defined by the OSI model. Now, when we're working in networking, do I care that the Citrix ICA protocol and the SSL protocol don't operate at exactly the application layer? Not really. Working as a network engineer, we don't really care if Citrix ICA is presentation or not. As network engineers, you're going to be most concerned about those first 4 layers of the OSI model or the first 3 layers of the TCP/IP model. My experience as a network manager for a team of engineers has been that if the engineers can prove that TCP at the transport layer is moving the segments back and forth correctly, everything else is an application layer problem, and it is not something typically that the network engineering staff can deal with. So from a CCNA perspective, do the session and presentation layers matter? Not really. Are there protocols that exist there? Yes. For the purposes of this course, we're not going to worry too much about separating out presentation and session. We're going to use the TCP/IP models version here, where anything above the transport layer is an application layer protocol. To wrap this up, what we did was we mapped our communication dissection from the previous model to very real things in data networking. We took a look at how those very real things in data networking map to this very old OSI model, and as well as how they map to the newer TCP/IP model in data networking. What we're going to do next is we're going to look at how the data is actually encapsulated inside of new messages using the TCP/IP or OSI model as our guide through the process. Thanks for watching. Let's move on to the next video.